In this lab, I dropped an object from rest and I found observational data for position of the object, and I created two computational models to compare to the observed data. So in this experiment, I estimated the mass using this process, and I used the width of the object to calibrate Tracker. So when I put the video into Tracker, the motion was in the negative y direction, as can be seen in this plot here, and I was able to find the initial position vector and the final position vector, as well as the change in time. So because this object, when I drop it from rest, has forces acting on it, I used Newton's second law to connect it to velocity. So Newton's second law states that the change in momentum is equal to the net force times delta t, and change in momentum equals mass times change in velocity. And so from there I was able to get to this position update formula here. And because the net force on this object, which I am going to be considering drag force and gravitational force, because the net force is only in the y direction, I only considered the y positions in the y directions. And so I have the final position vector equal to the initial position vector plus average velocity times delta t, and I calculated that to be negative 3.58545 meters per second for the final velocity. And so I was able to use that to create a model in GlowScript to create predictions for data, for the position time data, if I were just considering gravity as being the net force. And so here I inputted all this information, and it's starting from rest, so the initial vector is 0, and the proportionality constant b is equal to 0 as well, because I'm not considering drag force, and I use this while loop to update the velocity based on the net force and update the position based on velocity. So when I run that in GlowScript, I get the motion of the object, and the position versus time graph is curved downward, and the velocity versus time graph is linear because the velocity is constant since net force is constant. In the second model, I incorporated drag, so I have a proportionality constant of 0.04, and I calculated the drag force to be the velocity of the ball in the y direction squared times the proportionality constant, and I added that to the gravitational force to get F net. And the drag force is in the direction opposite to the direction of motion, so it's on this positive y axis. So when I plug that into GlowScript and I run it, I get similar motion here, the position versus time graph, and the velocity versus time graph, which has an asymptote because the velocity is approaching this limit here, and that limit is the terminal velocity. So terminal velocity is when the magnitude of the drag force is equal to the magnitude of the gravitational force, and at this point F net equals 0 because the drag force and gravitational force are balancing each other out, so the velocity would be constant. Only the model that factors in gravity and the drag force would predict a terminal velocity, because in the model that just has gravity, the net force would not equal 0 after the object has been dropped, since there's no force counteracting the gravity. So that's why we see in that model with the drag force an asymptote, because it's approaching this constant velocity. So when we compared the position time data plots for the three options here, the observed data, the predicted without drag, and the predicted with drag force models, there are significant deviations. And in particular, though the predicted model with the drag force is a bit closer to the observed data, it's still a bit different. There are differences. And I think those are because there was movement of the tissue as it fell. Although I dropped it horizontally, it did turn around, and I think that was not captured well in Tracker. And the low frame rate also led to these plateaus in the plot, so it wasn't a smooth curve. What if the object was thrown downward? So in the model with drag force, I set the velocity of the ball equal to -2 in the y direction, and I got this graph. So if we compare it to the velocity versus time graph when there's 0 initial velocity, we see that the asymptote, the velocity value of the asymptote that they're approaching, is pretty similar, around -2.15-ish, but the times are different. So when there's a non-zero initial velocity, the object approaches that terminal velocity faster than it does if there's a 0 initial velocity. And this makes sense because we've set drag force equal to object's velocity squared times the proportionality constant. And so if it starts out with the larger initial velocity, the drag force will be larger to begin with, and it will be able to increase a bit faster and balance out the gravitational force more quickly.